today. Welcome back. I'm Kathleen Kennedy. I'm an associate professor in retailing and consumer sciences, and I'm going to be moderating today's professional development panel. Let's start with some introductions. Anna?
Hi everyone, I'm Anna Josephson. I'm an assistant professor in Ag and Resource Econ.
I'm Amy Hudson. I'm a PhD student in School of Natural Resources in the Tree Ring Lab.
Hi everyone, I'm Nazo from Agriculture and Resource Economics. I'm assistant professor of practice.
Hi, I'm Jean Zhou. I'm assistant professor of biostatistics from College of Public Health.
All right, I put together some really tough questions today. I came across a description of the ideal candidate in an active, unfilled position. The ideal data scientist has hands-on experience developing data science solutions, ability to communicate effectively with non-technical stakeholders, has experience with coding language, and understanding of advanced statistical models, predictive analytics, and machine learning techniques. There are many more open positions with similar requirements. I'm going to start with Na. Do you believe that the need for data scientists trained in multiple disciplines will remain the norm, or will there be a shift to data science teams composed of specialists?
Okay, so I think you posed it as actually an economic question. The idea here is in economics, we believe in specializing in labors. So basically, we like the idea that if you are in a field and you specialize in it and you are good at it, it will promote the economic efficiency, and based on that economic efficiency, then we skill up, get the economic of skills. So that's how I say it when it's rolled out in industry. But when we talk about like academia or working, like I feel like interesting question is always inevitably multidiscipline, so that kind of a background of knowing a little bit everything and be able to communicate, that is very important. So yeah, that would be my thought.
Since I got an economist's answer, I'm going to flip it over to Anna. Do you agree with Na?
Generally, yes. I actually read the question in the same way. I was like, oh, specialization versus diversification. The one thing I will add is that I think there's some assets to knowing a little bit about a bunch of different things, particularly in communicating with your team. And so you might know the most, you might specialize in one particular area, but being able to say, oh, I understand what you're saying in your specialty, I think has a good asset.
Jen, anything that you'd like to add to that?
Well, I think that's definitely true that you need to be multidisciplinary. And also that can, like, related with my question is that how can you build yourself strong enough to be a data scientist? That is definitely another part that you need to build upon, that to be able to communicate with different people.
I'm going to go in desperation for one last person. Amy, can I get you to root for teams? I didn't realize this was an economic situation.
Yeah, I'm pro team. And hello. I'm pro team. I use data science to promote and manage my own science. So, and I also use a lot of different data streams where we have people who are experts on the uncertainty of us, like flux towers, or someone who knows the uncertainty of looking at photosynthesis at the leaf level. So I think being able to communicate in a team environment and to communicate that between data scientists is really important.
Thank you. I honestly never did well in economics. Jean, I've got a question for you. Data science is a field with a huge demand. We've heard that in every presentation I've seen about data science for like 6 years. In part because it seems to require experience as a data science to be hired to be a data scientist. What strategies can an aspiring data scientist use to build meaningful experience?
Okay, so I will approach this question in, I guess, 3 ways. First, to be a meaningful data scientist, I think you definitely need to know the data. So depends on what field you will be as a data scientist. The data will be collected differently and under different kind of study design and with their own features. So if you are thinking that you, after school, that you can automatically be a very good experienced data scientist, that's probably what will be very stressful if you go on a career. So I would suggest in school, you first of all need to do some data analysis type of work just to know the data and to be able to use your skill sets to apply on this data so you can do things and make some conclusion about it. So then that's related with my second point is that the skill set. So I am a statistician about statistician. So definitely statistics is the key here that you're approaching the question and the uncertainty of the questions and make some conclusions, association, causal, so on and so forth. So you definitely need to have those skills, and that is also related with math. So that is you can learn from the coursework and be able to talk with different people and express and interpret the knowledge that you learn. And I would say that for my experience, I also would suggest for some algorithm type of coursework is also important so that later on you may need to analyze some gigantic data. And just not running some pipelines, you don't know where the efficiency cost is. But if you are able to just know some algorithms, computing algorithms, statistical algorithms, optimization algorithms, so you can diagnostic how can make work more efficient. And then third thing I would say is the computing skills. I taught introduction to healthcare data science course last semester, and in the course I will always say that I suggest people to know one statistical computing type of a language, like R, or like I'm using Julia nowadays, or MATLAB. And then you also need to know scripting language, like shell script, to be able to communicate with the Unix within the Unix system. Another thing I would suggest is the database type of language, query type of language, SQL, and be able to understand how the database was built. Related in healthcare is medical records, how the medical records were stored. And just for example, there must be a lot of others, but the basic system-wise is probably the same. But just be able to know that. So for those 3 aspects, I think are the most important thing that I would think. That's just build yourself strong. But in order to be a data scientist, to find a real job, that's another story. Then you need to build up your CV and have some network and like the related with previous question, you need to have very good communication skills.
Thank you.
Thank you.
Anna, see if I can trick you up. Data science is a dynamic field with very specific requirements that are constantly changing. What's the best way for a data science professional or someone aspiring to become a data scientist to maintain their credentials and update their skills?
So I was really excited when you sent me this question because my partner and I are learning Julia right now, and it is not going well. And so this question made me take a step back and say, okay, why is this the programming language that we decided to undertake as a learning project? And we actually picked it because we read about it on Twitter. And I realized that Twitter has this incredible community of economists who are talking about the work they're doing, what they're learning, and why they're doing it. And I take a lot away from that and what I can use to move forward and to what projects I should be undertaking to keep my skills up. And I have to imagine that there are a lot of other fields that have similar communities on Twitter. I know I follow Leslie, who's an epidemiologist, and she has Epi Twitter. We have Econ Twitter. So I hate recommending Twitter because it's like, here, take on something that will constantly distract you away from more important work. But it really is a good community for learning about what skills other people are doing. The other thing is, when you're learning a programming language, it's not always very fun. And making sure you have a project or a reason for doing it other than just, this is something I should know. So when I was in college, I needed to learn Java. And I tried just learning it cold. And then I found a program where you can battle robots against other robots by using JavaScript. And that's how I learned Java, because I was really excited about making this code bot that would go out and battle, and it lost a lot, but eventually I got better at it. And so finding the thing that makes you excited about learning these new skills, other than just building up your CV or being able to write down that this is something you can do, I think is something that's really valuable. And knowing what's right for you. Like Jen was talking about, these are the 3 things she sees as needing to take her career forward. And those are going to be different depending on what field you're in. And knowing that, I think, is really important. So,
Thank you. Data science is a diverse area composed of many specialties. Data engineering, data mining and statistical analysis, cloud and distributed computing, machine learning, cognitive computing, and so on. What approach do you recommend taking in selecting and building a specialty? Are there any data science specialties that you believe are more open to women?
When I received this question, I was blown away by how many data specialties are out there. I think I'm not that surprised, but that's how we kind of specialize ourselves. But I have to admit, I don't know all of them. But what I can say is that to find the area to develop your specialty, it's really the question to one individual from your own interest. So I can relate back early on when I was back in China trying to learn English, and I feel like I enjoy English, but I never, no offense to English major here, anyone, but I never thought I will pick English as my college major or later on major, because to me, English is just a language for me to communicate. But the content of my communication is the domain, is a specialty, is a field that I'm passionate about. So that's why I choose economics and use English as a tool for me to study here and teach here. Now, I think the similar way as data, the idea here is data is really a language for you to communicate with other disciplines and with other field. And I will amazed to see actually we share so many basic data science principles across field. It's just the techniques, the softwares, the different, the technical part seems so different, but I would think find that domain that interests you. But if the data science itself is a domain, for example, you really want to advance the software and the computing power for other fields, and if you really advance the mathematics in the principles, that is your domain and the tool as well. But for me, if I see it as a tool, I find that field I really love, and then figure out what, like Anna said, figure out what other fields are using in advance. in the data management or data tool so that to complement my specialty in the field. Now, the second part of the question is about any field is special for women. I guess I did a little bit research on that. I cannot say which specialty, but I know that our university academia has a higher share of women in our STEM or data scientists comparing to industry, comparing to the business. So I feel like a university is an open, very open environment, and I enjoy it, but it's not for everyone, I guess. I guess goes back to our keynote this morning that try to find our strengths first and be present and be confident, and then go to the field you feel you belong.
Thank you. Very nice answer. Amy, I saved the hardest one for you. Only 15% of data scientists and about 25% of predictive analysts are women. What should the University of Arizona, our faculty, students, and community supporters do to encourage more women to pursue degrees in data science-related disciplines?
Yeah, my initial thought that I'll just put out there, because I think a lot of people are thinking it right now, is create equal pay opportunities. So I'll just say that.
Yes.
But,
Yes, please.
but beyond that, you can't be what you can't see. So events like this Women in Data Science event, I would like this to be an annual event that we do every year. Maybe even more often than annual. And I'd also like to see from a top-down approach, we're having this, so I'm a data science ambassador, and we're trying to, I'm one of 8, and I'm with the College of Agriculture and Life Sciences, and we're trying to promote resources out in the community about what's available to people to improve their data science skills. So I think that that would be great to have on an organized level, and I think that's what's going on right now in Data Science Institute. Also, we're creating a survey to hear what the need is within each of our colleges in terms of data. Jolly is also another data science ambassador. So hear what the need is from the groups in our community, in our U of A community, and then determine how we can provide for that need from the top down. But from the bottom up, I think it's also important to take up the space that you want to. So I wanted to have more coding time this semester, so I asked our staff in the Treering Lab to help me reserve a space in our conference room, and now the whole community is welcome to code there for 2 hours on Tuesdays every week. So I think it's really important to know that you can make an individual impact and have people bring questions and build up from the ground also, not just top down.
Thank you. Now, a question for everybody on the panel. I'm going to start with Anna. We have a number of women and a couple men here today who might be at the beginning of their careers or might be thinking about switching their career to pursue a career in data science. Do you have a secret success that you would pass on to somebody who's thinking about either starting a career in data science or shifting?
Oof. I will confess, I did not prepare anything beyond my initial question since we only had 30 minutes. But I guess my advice is to make a lot of mistakes and do things you are not very good at. I am not very good at math, but I've spent a lot of time doing math and practicing math, and I think I'm pretty good at math now after a long time. But I wouldn't be an economist if I was no good at math. And so to diversify from doing what I was doing to being an economist required me to practice a lot of something that I wasn't good at. And I think the same applies for data science. You might not be good at coding. You might not be good at managing large data sets or managing small data sets wherever you're at, but making the mistakes that need to be made in practice.
Let's go ahead down the line. And Amy, you want to give a secret?
Yeah, well, I'm really enjoying these coffee code hacky hour times. So interacting with people outside my field is helping me learn a lot Yes.
Okay. Nah? Big secrets. The stuff you don't want anybody to know because they'd be more competitive with you.
I totally
I
didn't say
framed
this.
that as an economics question. I want to point this out.
I feel like the secret is make it sound like as long as you do this one thing, you will be successful. But the thing is, there are so many, and now I think about that, and I feel I I I think I would have to agree with Anna. I really agree with Anna on this point that I emphasize on to find your own interest in my question previous, but I would follow up on that, that once you find that, don't be discouraged so easily. Because from interest to learn something, to be a specialist in one field, that's hard work. So I guess find the interest, and I even back off in the way that if you don't find the interest, for example, if you are in the graduate school, you have no idea yet. You may have some idea about your dissertation, but you don't know beyond that. That's okay. That's okay. To me, the important thing is you are trying. And anytime I take on something new for myself, I will tell myself, the worst it can happen is that after this experience, I realize, okay, so I'm not so good at it, and maybe I need to work more on it if I really to pursue it, or I just change. So I always find it's always a good result from a new experience, no matter what. So I guess that if that answers the question.
It was fine, thank you. Jane, is there anything that you would want to add to this?
Sure. So I feel like data scientist, this name is a big umbrella. It covers lots of things. I would suggest that we definitely need to be ourselves. We need to find our strengths, the uniqueness of yourself, that it's you, that nobody can replace you with other person. So I think that's really important to know what you can do, what you are good at, and what your training that in the future that you're in the company is a big gigantic machine, but it definitely needs you. So I would inspire all the women that to find that part of yourself and to be brave and to pursue it, and know, I mean, there are discouragements, but just go ahead. We can do it.
Thank you. That's a wonderful way to end this panel up. I want to thank Anna, Amy, Na, and Jean for taking the time to do this and share some of their secrets with us. So thank you so much.
All right, wonderful, and you did perfectly on time. Everything is great. I want to mention a couple of things before we move to our next segment. In the current panel, we heard people talking about Twitter, and I neglected to put this slide up. So if you do use Twitter, please be tweeting today about this event. And also around the room, you might see these signs with the little yellow ghost. If you use that, I don't use it. I guess it's Snapchat, but if you do, please put the word out about what we're doing today. And the other thing that I wanted to mention is about lunch, because our next segment is going to be a data blitz. We're going to hear lots of really exciting 3-minute talks about data science. And then we're going to have lunch, but lunch is going to go this way. We have these poster boards taped up on the wall about different topics: increasing your confidence, building a women's data science community. I can't quite read the one in the back, but I want you to mill around and talk to the people who are sitting next to those boards. And because of that, the way we're going to go to lunch will be brought in back in the back where those snacks were, is the people who are presenting the conversation, the little breakout tables are going to go and get their lunch first, because otherwise they'll never get there. Then anybody who needs a vegetarian or a gluten-free lunch is going to go next, and then everybody else can go grab. There's going to be 4 different choices for lunch, so hopefully everybody will find something they can enjoy. And now I'm going to turn the floor over to Joanne Burkhout, who's leading the DataBlitz, morning DataBlitz.
Yeah, so I'm actually
Oh no, this one's kind of green.
okay, if you guys can take your seats and get settled, we are going to begin the DataBlitz talks for today. So I'm really, really excited. We had such a fantastic group of women submit talks that they're going to showcase 3 minutes of data science, or how data science intersects with their work. And one thing you're really going to notice, you may get whiplash noticing it, is really how many different topics are covered here at the University of Arizona. And it's really, I think it's going to be great. I don't want to take any additional time. Each of the speakers will come up, introduce themselves, give a very, very rapid talk. We don't have time for questions during this section, but I've invited, and hopefully all of the speakers will be sticking around during lunch. I've met most of them. The rest, I'm sure, are equally friendly. Do go up, say hello, ask your questions then. I'm sure they'd love to talk to you. So without any further ado, I will turn the mic over to Bonnie LaFleur, who is with the Bio5 Institute, to get us started.
Good morning. Okay, I'm going to start. This is going to be really hard, but I'm going to do it because I think it's important. And I just want to tell everyone I have a poster, so I will be over. This is going to be really fast, so come and ask me questions later. But what I'm going to talk about today is combining predictive models. Everybody here does predictive models of some sort, it's likely. What I do as a statistician is try to use those. So I'm more focused on the interpretive part. So here's the problem. We have to actually help patients make decisions. And it's oftentimes, we all know how to do modeling and get those predictions, but how do you turn those into something that somebody can use to actually decide something? And from my research, it's should I take a treatment or not? This is more difficult when you're doing individual predictions than it is if you're doing group-wise predictions. That's one thing. And the second thing is when you're making predictions about a single outcome, it's a little bit different from making a decision that combines both the outcome that you're interested in and also the risks of not doing something. Okay? So this is a novel model assessment tool that we developed. We call it, and we use combined benefit. And it's based on formal statistical decision theoretic framework. So we're actually just using usual decision theory, which statisticians learn a lot about when we get our PhDs. And it actually combines this prediction with treatment not doing something. Negative side effects, how much it costs, how much time it takes. So I can summarize what we did by looking at this graph, and I'm going to explain a treatment decision. If a patient has an adenoma, which is a precursor to colon cancer, and they have a choice of taking a chemopreventive agent after the initial resection. Okay, so we had a clinical trial of patients who were randomized in this situation, and they were followed up for 3 years to see if their adenoma had recurred. Now, the challenge here for this particular solution was that people responded really well to the chemopreventive agent, and it worked so well that we had very, very few recurrences in the treatment group. Great for patients, not so good for us as we're building a model, because what I'm showing here in this blue line is the actual prediction model, and I'm comparing that prediction model to not treating anybody or treating everybody. And this area here in pink is like the area that would denote whether or not this is a good treatment. Well, the challenge is everybody did well. So in an ideal situation, we could use this to identify a group of patients for whom they might have experienced a low recurrence, but it might have been a risk. Okay, so come and talk to me at the poster session, and I will give you a lot more information about this. Thank you.
Hello, thanks for coming. I'm Amy, and I'm a PhD student in statistics GIDP and also a member of UA Tripods. I'll talk about some challenges of cancer diagnosis and how we can use machine learning techniques to resolve these issues. So there have been extensive studies addressing some problems of pathologists' inconsistency in different types of cancer. And some of the problems that they address is that pathologists make decisions that are subjective and conservative. For example, ovarian cancer, women in younger ages, they have to remove their ovaries upon the diagnosis of ovarian cancer, because even if there is a small chance of cancer, the doctors will recommend to remove ovaries. Also, pathologists' practice takes years of experience and expensive trainings. So we want to develop a more quantitative, objective, automated, and precise methods using machine learning techniques. So we use karyometric analysis, which provides a more objective and quantitative ways to measure cancer cell characteristics. It starts from the biopsy of tissue samples and microscopic analysis, and it extracts some features that includes size of nucleus, roundness, optical densities of cells, and so on. So our goal is to develop machine learning methods that can correctly identify these different types of cells. This graph is from the previous studies, and if you look at, and it still has some problems of using machine, it has some problems to be resolved. If you look at the third row, if the machine learning correctly identifies the case, we have to have the higher bar for the blue ones. But if you look at the cases 2, 4, 8, and 11, sometimes the machine learning tell you that this patient has, its patients are normal, even if they have cancer. Or for cases 2 and 4, these people are just at risk of cancer when they actually have cancer. So we want to develop machine learning techniques that can automatically learn patterns in cell images. Also build a classifier, which is the subset of karyometric features that we get from the karyometric data that can accurately identify cell types, which can distinguish normal cells and cancer cells. Also, we want to achieve computational efficiency and have solid statistical theories. I have a poster session in the afternoon, so if you have any more questions and suggestions, please come by and talk to me. Thank you.
Hi, everyone. I'm Hong Cui. I'm from School Information. Today, I'm going to use one slide to talk about my research work. Oops. My research can be summarized in one sentence: to turn text into computable data. What computable data mean in this context shall be clear in a moment. So in biodiversity domain, there are lots of fact information being published all the time, describing living or extincted organisms, ecosystems, climate change, etc. Those information are presented in a human language, so the computers cannot directly use them. The first area of my research is to do text mining, machine learning, natural language processing, where we use those tools together to extract the factual information from the text. We develop softwares and we evaluate them, they're listed here, we turn those information into a tabular format. Those tables are very useful because it has facts separated into different columns, but they are not yet computable. The reason being that the terminology people use to describe those facts are as diverse as the biodiversity themselves. So our next problem is really data standardization and data integration. Our approach to data integration is a semantic web-based approach where a formal conceptualization of a domain is constructed to describe the entities and the relationships about those entities in detail. Our task here is to link natural language facts to those entities and relationships in formal ontology. We developed a ontology building tool. We developed algorithms that actually help us to link natural language facts to formal ontological statement. So at this moment, the data becomes computable because we can programmatically compute the similarity between data points. We can actually use machine to infer, to find conflicts in the data set, or infer even new facts. My research could don't be here. I mean, I could spend my entire year working on those two problems, but in one of the evaluation, we found a sad fact that actually either machine or human expert can accurately translate published scientific facts into a machine format with accuracy. That the translated statement may not truthfully reflect the original meaning of the author who documented those facts. So that goes to our current project that we're trying to put the authors in the driver's seat, where we develop tools to help the authors to actually create computable data at the time of the publication. That's it. Thank you for your attention.
Hi there, I'm Marina Kiseleva, and I'll be presenting today on predicting astronomical transients. And it's actually a collaborative project between the Department of Astronomy, Physics, Computer Science, and the Data Science Institute. So to get started, really quick, what are transients? So transients are actually really big explosive events in astronomy. So think of like supernova or matter falling into black holes. There are these really crazy things that happen, and they don't happen that often in the big scheme of things. And unlike most things in astronomy that happen over the course of millions and billions of years, transients only happen over some days or weeks or months. So they're relatively quick. And they're a very important object of study for astronomers. They're so important, they're one of the main objectives of the Large Synoptic Survey Telescope, which is a new telescope that'll be launched soon, that'll be able to see even more transients than ever. And in fact, it'll see a little bit too many. It'll see up to 10 million transient events a night. So we don't have 10 million telescopes on Earth to go point in all the directions to look at all of them. So we need to somehow prioritize the most important ones. And to prioritize these events, we have to figure out which is which and which is more important than the other one. So that's our machine learning classification problem, is figuring out what type of transient is happening in which part of the sky. And the most obvious solution is to take the information about the transient and categorize it. But that doesn't necessarily work right away because we need to wait to gather enough data about the event, right? So instead, our idea is to use the galaxy's information about the event in order to predict the event before it even needs to happen. So what this means is we want to figure out, based on a galaxy, this is the spectra of a galaxy, so simply how bright the galaxy is in different wavelengths of the electromagnetic spectrum. Based on this type of galaxy, what transient is most likely to happen there, and the probability of different types of transients. And ultimately, when we're finished, we want to have a tool that can tell us what transient will happen in what galaxy before they even occur. We don't need to wait for the transient to happen. So the second that this telescope tells us a transient happened, we can tell, well, it's a probability of 85% it's this type of supernova or that type, right? And ultimately, because it's astronomy, I can say that it'll hopefully tell us the secrets of the universe a little bit faster. Thanks.
Okay, perfect. Hi, I'm Isabel Williams, and I'm in the School of Government and Public Policy. So I take a little bit of a different approach to data science, but I'm really happy to be here and inspired by all of these amazing women. So my project is about state legislative professionalism and its impact on immigration policy at the state level. So one of the issues is that in the US states, professionalism varies dramatically across states. So that could be, in some states, legislators have the salary, the resources such as legislative staff, and the length in legislative session to be more like those members of the US Congress. Whereas in other states, it's a more informal approach. Their pay is symbolic. They may even have a full-time job in another profession. And so they have a different set of limitations upon them. The issue that we have in studying these outputs, policy outputs, that may be affected by this institutional format is that they're not randomly distributed throughout the state population. More liberal states are often the most professionalized, whereas more conservative states are often the least professionalized. So we have an issue with multicollinearity going on here. So I use the National Conference of State Legislatures database, and my partner and I are hand coding many laws from 2011 to 2016. We're focusing on laws that affect undocumented immigrants. And so our unit of analysis is state legislative session. Is typically 2 years, and it begins at different times for different states. So that's how we look at that. So the way that I'm attempting to overcome this problem of multicollinearity is to use a propensity score matching technique. And this is a bit controversial, so I'm hoping for maybe some feedback right now, which is that this will create a data set in which legislatures are compared with being above or below average levels of professionalism, but they're comparable on other types of covariates like ideology. So the ultimate goal is to look at the dependent variable, which is the tone of immigration policy that's coming out of these states, and be able to look at that across the more professionalized and less professionalized state legislatures. Because ultimately, this is an issue that is about democratic representation. So as citizens, as people that belong to a state or are hoping to be incorporated into a state, we care about what our legislatures are producing. And these institutional factors may have an impact on the type of policy that we're able to achieve. So that's what I'm working with now. Thank you very much.
Hello, my name is Lavanya Mapati, and I'm a PhD student in electrical and computer engineering. Magnetic resonance imaging is a non-invasive and non-ionizing imaging modality that is widely used in the clinic for the diagnosis of a wide range of pathologies. I'm going to talk about neuroimaging in specific. Here is an example of a brain image that has white matter lesions in it. And the extent of these white matter hyperintensities in the brain has been associated with an increased risk of stroke or dementia. Now, manually annotating these white matter lesions to find out the lesion volume is very time consuming and is very challenging. So our goal is to use a deep learning network for fast, accurate, and a reliable technique to automatically detect white matter lesions in MR images. So the first step is to design a deep learning network. Now, this network consists of a set of parameters that can be tuned to perform a specific task. In this instant, we wanted to take MR images of the brain and tell us where the lesions in the brain are. Now, these predictions can be compared to a ground truth, and the errors in the prediction, errors between the prediction and the ground truth can be used to tune the parameters in the deep learning network. The next step is to train this network, and we give it thousands and thousands of images with lesions marked on them so that the network can understand which regions of the brain have lesion in them and which do not, and such so that it can drive the predictions closer and closer to the ground truth as possible. And the next step is to evaluate. So here's an example of a brain image that this network has never seen. The annotations are from an expert neuroradiologist, and the prediction from the deep learning network is shown. And the inset is shown in the right panel, and you can see that the lesions are overlaid in red or on the image. And you can see the predictions for these white matter lesions are very close to the expert annotation. And the deep learning network is able to make these predictions in less than 1 second. Our objective in this is to expand these detection strategies to other MR imaging applications, to look at the progression of disease over time. We've been able to use similar detection strategies in identifying prostate in body MR images. The idea is once you have these regions detected, you can look at features from these regions and try to find out what kind of pathology is it and how it will progress over time. Thank you so much.
Yeah. Yeah, okay. So I need to change here. Okay.
Hi, I'm Francesca Vitali. I'm a research assistant professor in the Center for Biomedical Informatics and Biostatistics in the Lucia Group. And this talk is about a matrix factorization algorithm to identify patient similarity and subgroups. So patient similarity is a kind of already used in clinical practice. For example, when a patient, when a patient goes to a doctor, he explains his symptoms and other data are collected. And the doctor tries to make a diagnosis or prescribe a treatment based on this data. And therefore, he considers them also in relation to patient that he previously visited. And this in order, for example, to identify which patient is the most similar to the one that is currently visited. However, in this way, you can, for example, prescribe the same treatment or make the same diagnosis for the new patient. However, this may be biased by the time because a doctor may remember better patient that he visited more recently if compared to the one that he visited further in the past. And currently, we can leverage on machine learning technique, for example, data fusion technique, that are able to integrate large quantity of data and also different type of data, such as clinical data, health records, and exposomic data, and automatically compute patient-patient similarities. And these can be also helpful for precision medicine. In fact, for example, if we find two patients that are similar, is more likely that the same treatment would be efficacious for the two similar patients. And here we propose an approach that is based on the representation of the data sets that we want to integrate into a matrix form. So each database is transformed into a relational matrix that is going to be a block of a bigger matrix. And this big matrix is, in this big matrix, we are going to represent all the relationship between the object involved in the data source that we included. Here we wanted to include, for example, clinical data, genomic data, and other source of knowledge. Then we can apply the non-negative matrix trifactorization algorithm that basically transform the matrix and into smaller matrices that are that represents the original matrix into a lower dimension. Then through an iterative algorithm that minimizes a cost function, we can obtain a new block matrix that is the reconstruction of the original one. But in this matrix, we are going to have a novel prediction and patient similarities based on all the data that we integrated at the beginning. Okay? And here there is an example of the output. And for example, so we can have a cluster of patients, and we currently applied it to acute myeloid leukemia. And we show that without including the survival information, the trifactorization algorithm was able to discriminate between poor and bad prognosis. And if you want to know more, I'm going to have a poster outside. Thank you.
Hello, I am Elahe. I'm a postdoc in UA Cancer Center in Thorne Lab. Today, I'm going to talk briefly about my project, which is how I harness phenotypic complexity to predict kinase function. So in a genomic area, we can list all the kinases, but we do not know all their function. With high throughput screening, we can study all kinases at the same time. So this is our approach. So what we do, we culture cells in a bunch of 96 well plates. In each well, we knock down one protein kinase, and we capture an image of the cells. This is, where's the, I can't point. No, these are, so this is the images that we have, and then we segment the cells using a software to identify the cells and the boundary. Then we calculate some features, which are like some features like area, perimeter, and these goes on. Like we have 509 features, and it starts with simple features, but it becomes complex. Then we cluster all the kinases into different groups which have different morphology. And then, so these kinases are we have some well-studied kinases, and then some that are not categorized. So our hypothesis is that the cells that are in the kinases that end up in a similar group, in close to each other, have similar function. So if it is true, we can predict function of uncategorized kinase based on function of well-studied kinase just next to it. I have a poster. We can talk about this more if you are interested. Thank you.
Hi, everyone. My name is Jali Han. I am a PhD candidate of the Systems and Energy Engineering, and I also gained a master's degree from the Statistics GIDP. So I feel so thrilled and more than happy to have the opportunity here to share with you. And I want to thank all the great female professionals to make this conference happen, and especially Susan. You thanked everyone, but you will never talk about yourself. So I grabbed the opportunity for thank you for taking the huge extra workload in the past months to make it all happen. So this is actually the tentative title of my thesis. So it is large-scale heterogeneous omics data analysis in revealing convergent genomic risk of human disease. So the problem that I am going to answer is to me, the challenge of interpreting the functions of the non-coding SNPs, which is also the genetic variants. So these non-coding genetic variants, they account for more than 98% in human genomes. They used to be regarded as junk DNAs. We do not know what's their functions, but for the recent decades, we are finding that they have regulatory functions in our genome to encode the proteins. So the tools and approach that I use is I first integrate the multiple encode datasets to discover the genomic functions of the non-coding SNPs. So I integrate more than 300 datasets of the Encyclopedia of DNA Elements, which describes the functions of the non-coding genetic variants. And the whole data size is above 300G, which is out of the capacity of my own Mac. So I use the HPC to do all the calculations. And then I exhaustively search all the genetic variant pairs to discover if they have convergent genetic risk to human disease. So I searched the more than 1 billion genetic variant pairs, and we wrote a pipeline combining the programming tools of R, Python, Linux, and also we use the Julia to wrap all these code all together to build a pipeline. So the results will help to understand how the genetic variants in our human genome will interact with each other, and it can help identify the genetic-specific molecular targets and inspire new personalized therapeutic strategies. And a little bit about the advertisement of myself. I'm about graduating this year, and I'm going to look for a job in the industry as a data scientist, of course. So if there's any kind of information of job opportunities, I'm on my ears, and I will be so appreciated. Thank you.
So hello everyone, I'm Chunan, and I'm a PhD student from the Department of Biosystem Engineering. So today I will talk about my research on the gene co-expression network analysis of type 2 diabetic skin disorder. So the type 2 diabetes mellitus is a kind of long-term metabolic disorder, and the main characteristic is the high blood sugar, which can cause the nerve damage and vascular disease. So with the loss of feeling lower legs and the poor blood flow, about 30 to 70% of the patients will have the skin disorders such as infections and chronic ulcers. So the problem is, what are the molecular mechanisms behind such phenomenon? As we know that the gene encodes the proteins, and the proteins enable the cellular functions. Instead of working alone, studies have shown that each gene is estimated on average to interact with about 4 to 8 other genes and to be involved in 10 biological functions. So, for example, like the hemoglobin synthesis requires the coordinated production of heme and globin. So that's why the gene co-expression is really important to our human health. And gene network is a really good method to describe a complicated and large-scale gene interactions. So this is a network I generated which comprised about 700 gene nodes. So the links are represented by the pairwise expression correlations. And within the network analysis, we can figure out the important co-expression patterns and the genes, the help genes behind those patterns. So my goal is to detect the differential expression genes between the type 2 diabetics and the patients and the people without type 2 diabetes. And then with the network analysis, identify the co-expression gene modules and their related biological functions. At the last, I want to look for the potential disease genes that can lead to the diabetic disorders. That's it. Thank you.
Courtney, am I in the wrong order?
Sure, yeah, I can go. Hi, I'm Courtney Giebink. I'm a master's student in ecology and evolutionary biology. So forests, they provide a lot of ecosystem services, one of the most important being that they sequester carbon out of the atmosphere. It's estimated that they've sequestered about 25% of carbon emissions. But their ability to do that under climate change is kind of uncertain in the future. If we look at Earth system models, don't really need to know too much about this graph, but here we see that in the future, the projected forests are projected to continue to sink carbon through biomass, and some also project carbon to be a source from the land to the atmosphere. And so this carbon, it's uncertain, but it's really important because whether it's being in the biosphere or in the atmosphere, it'll feed back to the climate system. So that's really important. So our question is, will forests continue to be a carbon sink, or will they become a carbon source? Oh, sorry, can you hear me? Yeah. And so my work is using tree rings to really find this link between forests and climate. Tree rings are a measure of carbon sequestration, and they vary with climate variation. And so we have a data set, unbiased data set across the interior West that we're doing this with, forest inventory data and tree ring data. And so what I'm trying to do is a statistical model to really relate tree ring with climate and tree and stand variables. And so this model isn't just important for understanding carbon cycling, but it'll also be used to update forest management tools. The Forest Service currently uses the Forest Vegetation Simulator. It simulates growth, mortality, and regeneration to project a future stand. So if we have a current stand 2014, we can insert current variables, and it'll show what that stand is going to look like in the future. My model would update the growth models within this management tool to provide better projections of forests so that they can be managed more appropriately. Thanks.
Hold on a sec. I have something for you. Thanks. I've lost her.
So we'll have Emmy, and then I'm going to get 3 slides on a USB stick too.
Hi, my name is Emmy Bevensey. I'm a doctoral student. I'm not actually in my candidacy. I had to say that because it's on the paper and my advisor's right there. I study harmful content moderation and information wars between corporate and state actors. Particularly, I study things like hate speech, disinformation campaigns, conspiracy theories, botnets, things like that. So basically the issue is social media is being used as a platform to organize large-scale violence and to do targeted information war that impacts a number of major policy decisions. And the data sets are at scale, and the problems are happening live and right in front of us. and teams with HPCs and fancy degrees and high-paying jobs are not able to stop it. So it's a big open problem with a bunch of different fronts. So some of the ways that I study this is I look at basically the landscape of external links from hate forums and looking at where they're linking out to, where they're gathering, how they're mobilizing through social media. I map disinformation campaigns. Largely through Twitter data for that, and I do bot detection because a large degree of this is automated or semi-automated. We're finding that bots are putting out both conspiracies and hate content. So all three of these seemingly disparate areas are facets of the same problem. And I'm looking at why these problems are so hard and why everybody's failing at doing it successfully. And so I won't go into these too far because it's a short talk, but basically I have over here, this is some bot detection. Basically, I helped create a pipeline to find active users for a given hashtag and then try to figure out bot likelihood from within those accounts that are tweeting a lot. Here you can map disinformation campaigns. Here you can study sort of propaganda outlets and how what the different landscape looks like. And so basically my research helps to solve this problem and look at it from a bunch of different lenses. And I have a lunch talk and also a poster presentation later. So thank you. What's up?
Emmy, I had for you something for your participation. Thank you. Okay, so we're doing next. That was Helen's, I think. So take that out safely.
This is great. So my name is Bree Feingold, and I'm a electrical engineer, mathematician, data scientist person at Rincon Research Corporation here in town. It's a company that has been around for about 30 years. And when people talk about potential hiring, you can consider my company, where I love working for our company. So I'm giving this little plug while she gets my slides. So if you, no, it's okay. It's just a good opportunity for me to tell you how awesome it is to work here. And I realize most of the people here are from the university, but are there any electrical engineer PhD students? Maybe a couple here and there. So we're the 13%, right? That's it. Okay, so yeah, if you're interested in studying signal processing and geolocation, then you can talk to me. And what I'm working on is automatic classification of modulation types. So imagine all of the different airwaves that are, all the different signals that are coming through the airwaves from your phones, from television, from everything. They all take up a certain amount of frequency space. If we were to chop that up and then look see what's in there, try to figure it out just very blindly without like looking for a specific signal, like you may have heard different signal types or like BPSK, binary phase shift keying or something like that, some way of modulating AM, FM, all those things on your radio, then if you were to try to automatically figure out a way to identify just from some slice of frequency, some bandwidth that you recorded, what's in there, that's what I'm working on. And the slides don't add a whole lot, so it's not really important. There's a nice picture in there. So one of the things I use is cyclostationary processing. So you may know if you're a statistician, there's like stationary signals then most communication signals are actually not stationary. They do not have a mean zero and, you know, all that good stuff over time. So they are cyclostationary, which means that their statistics, although they change over time, they change in a predictable way. So I use that kind of analysis to come up with features. Now, that's one of the ways to look at communication signals and say, what are the features of the signal? You could say it's bauded. You could say what its center frequency is. You could say what its bandwidth is. And you can make pictures. And the pictures are kind of nice looking. And they also and they also help you figure out what types of signals you're looking at. So you can fish through. And the hope would be that machine learning, so this is a work in progress, so I haven't actually gotten a lot of results, but the hope would be that machine learning would sift through a large wideband data. Like you could have, you know, anywhere from like 5 to 900 megahertz, something data, like huge amounts of data, and look and find, oh, okay, here's a signal over here, and here's a signal over there, and this is the modulation type. This one's BPSK, this one's QPSK, and what all the different types are. So I really did submit slides, I swear. What else can I tell you that's interesting that you might appreciate? Oh, great. I heard this is looking hopeful, so that's good. Oh, right. Oh, there I am. Woo. Okay, this is the good slide. So I'll just switch to that one. Okay, so there's our emblem up there. Rincon Research Corporation. We're on Wilmot and Broadway. You can come by, but you can't get in. So anyways, the real question is, can machine learning somehow help efficiently survey large bits of swaths of frequency data? And this first periodogram is just frequency versus time. And so it's a raster, you know, FFTs of the signal over time. And it's like how many signals, even just from looking at that, you might say, oh, I think there's 2 signals in there, but there's actually more. That's just simulated data. And then if I take and do my magic cyclic processing, cyclostationary processing, this is where I'm going to get all my features. Then I get this picture, the spectral cyclic density picture, and that's frequency versus the alpha, which is the baud rate. So you can see that in there, there's something at baud rate, and my units are megahertz, so that's just like 200 kilohertz or something like that. So I have some stuff at that baud rate, I have some lower baud rate stuff, but it's much easier to see, and I'm hopeful that using frequency or using cyclostationary information will make it easier for me to distinguish and will make a better feature. Because right now what most people do is they make these periodograms, and because so much of machine learning is about image processing, image process data, and they shove those periodograms through the machine learning because they're like, it's a canned data processing algorithm that I can use, and it's not as informative as you would hope. So I'm also going to try to use higher order cyclostationary stuff. So that would be cyclic cumulants and time delay embeddings, because some signals are chaotic, which is like voice over AM. They're not predictable in the same ways. They have a carrier, but then your voice is not periodic. so then hopefully time delay embeddings, which is, you know, from chaos theory type stuff, would be useful. Has anybody ever used that? Because if you have, I'd really like to hear about it. It's something I read about that is used to detect arrhythmias and other you know, anomalies in, let's say, breathing and stuff like that, but I don't know a lot about it. But that's my take for the non-bauded signals, is to try to use this idea of a time delay embedding. All right, so my goal is to be able to explore signal space and reveal unexpected signals, things you didn't know were in there. Also to be able to identify bands not in use. That's what software-defined radios like to do. And lastly, to confirm the presence of signals you do think are there. Thank you very much.
Hello. Hi, everyone. My name is Marnie Dearman, and I'm the Chief Applications Architect at the College of Medicine. But today I'm here representing the Research Bazaar, which is an all-volunteer group on campus. We are a diverse community of programmers and researchers who are collaborating weekly to solve all of your worst programming problems. So some of you might find these statements sort of familiar, especially if you're a grad student. So the problem is that most researchers are not formally trained in programming, but you inevitably have to use programming in your work. So how do we bridge that gap? How do we get you the training you need to be effective and to get going and to be good researchers and data scientists? So with the Research Bazaar, we have events. We have a yearly unconference. It's called the unconference because it's sort of unplanned. It's sort of like we go to spaces and we have spontaneous collaboration, but we also have workshops and lectures and panels. And it's just a great place to go to learn and to network with other researchers and to collaborate with them. So that's coming up in May. And then we also have 2 weekly meetings. On Tuesday mornings, we have something we call Coffee and Code. That's in BSRL at the Catalyst Cafe. And then we have Hacky Hour on Thursdays at Gentlemen's. That's from, so the morning one is from 8 to 10, and the evening one, the Hacky Hour is from 4 to 7. And you can just show up. There's always tons of people there. There's experienced programmers and people who don't have much experience, and if we can't help you then, we'll find somebody who can. We also help put on the software carpentry workshops, the software carpentry and data carpentry workshops. I see some faces that I recognize from previous workshops. These are we do 2-day training intensive workshops in Python, R, and the command line, and then we have more intense short workshops. So our goal is to give you a place to go where you can get help, you can get training, and to give you a sense of community so you don't feel like you're going at it all alone. But ultimately, what we want are a lot of success stories. So here's Ariella. Ariella is a geneticist. Some of you know Ariella? So Ariella came to school here, and she inherited some really slow code, and it was going to take her 18 years to run her simulations on the HPC. So we're like, so she came to us, she found us, she's very resourceful, and we helped her make some optimizations to the code, and we did a lot of work with her, and we got her simulations down from 18 years to only a few months. So she was able to run all of her simulations and get her PhD, and she was very, very happy. And she went off to get her, she's working on a postdoc now doing what she loves. So these are our upcoming events. We have the conference in May. You can sign up here. I'll be having a table at lunch if you want to find out more, and I'll have some flyers too. And we have a website. And we're on meetup.com if you want to, you can find us there too. The Research Bazaar.
Okay, so that's it for our morning session of the DataBlitz. We will have an afternoon session with another great set of speakers. I want to thank all of our speakers again if we want to give them another round. Do you want to make any lunch? And I'll turn it over to Susan, who will give us what we need to know for lunch.
First, let's thank Joanne for that awesome DataBlitz session. That was really a lot of fun. Great to hear different things people are working on. And women are so awesome. I mean, I'm not usually on time as much as I have been today. So I think I'm like using up my whole year quota of staying on time right in this one day. So I just want to remind you, later the afternoon, we have a poster session. If you have not put your poster up, we are using both sides of the poster board. And there should be push pins on a picnic table out there. So there is still room for your posters. There are also some boards for announcements. If you have any flyers you want to put up or take a look at what's up there, take a look at the announcements. And I wanted to thank the Data Science Institute and Tripods and the Center for Biomedical Informatics and Biostatistics. I am going to learn that one of these days. But the three of them went together and sponsored our lunch in the back. So as a reminder, if you have a lunch breakout table, please go and grab your lunch right now and then get to your table. After those folks have gone, the people who need a vegetarian or gluten-free lunch can head back, and then the rest of us. So we will be back promptly at 1 o'clock to have another short data blitz. Thank you.